A New York sports writer claims the American League pitchers have lower earned run averages than National League pitchers. If 20 randomly selected American League pitchers have a mean ERA of 2.50 with a standard deviation of 0.15, while 16 randomly selected National League pitchers have a mean ERA of 2.60 with a standard deviation of 0.25, is the New York sports writer's claim justified at alpha equal 1%? Let mu sub 1 be the American League pitchers' ERA data and mu sub 2 be the National League pitchers' ERA data. So we have the sample size for population 1. We have the sample mean taken from population 1, and we have the sample standard deviation taken from population 1. Then we have the sample size for population 2. We have the sample mean taken from population 2 and the sample standard deviation taken from the sample from population 2. We're going to use a significance of 1%. The null hypothesis, we're going to state that there is no difference between the population mean ERA for American League pitchers and National League pitchers. There is no difference. Symbolically, mu sub 1 minus mu sub 0 equals, mu sub 1 minus mu sub 2 equals 0. So when you subtract two things that are equal, their value is 0. The alternative hypothesis is the claim made by the sports writer. The population mean ERA for American League pitchers is less than the population mean ERA for National League pitchers. So we want mu sub 1 less than mu sub 2, and if we express this as a difference, we say mu sub 1 minus mu sub 2 is less than 0. Okay, when you take a value mu sub 1 and it is smaller than mu sub 2, when you subtract the two numbers, you'll get a value that's negative. Okay. Again, my slide is a little messed up here. We are going to use the t-distribution because the population standard deviations for the two populations are not given. Okay, so in this example, like the ones preceded it, we don't have sigma, we have S for the two samples, and so we'll use the t-distribution. Since we have an alternative hypothesis that is trying to show that the population mean ERA for American League pitchers is significantly less than the population mean ERA for the National League pitchers, this is a direction. It's a test on the left. Okay, it looks like I'm missing the piece of information where I tell you what the sampling distribution, the mean of the sampling distribution is and its value. I must have missed it in the handout. It is, however, the same as what we had here. Okay, when we did example 13.2, let's see. Oh, okay, I'm sorry, here it is. When we did example 13.2, I stated that the mean of the sampling distribution is mu sub x bar 1 minus x bar 2, and its value is 0. I did not put this slide in after the last example, but it should be there. So I will add it now. Okay, so in example 13.3, you should also do the same thing. The mean of the sampling distribution and its correct symbol is mu sub x bar 1 minus x bar 2, and that is equal to 0. And the same with this example that we're doing right now, example 3. Okay, in example 3, you have the same thing. The symbol for the mean of the sampling distribution is mu sub x bar 1 minus x bar 2, and its value is 0. Okay, so I'm sorry I left that out of, that's on your handout, but it wasn't here in the presentation. It's here now. Okay, and we specified we're going to use the t-distribution. We also specified that our test was going to be on the left, and now we're going to create our decision rule based on the direction, or rather based on this picture showing alpha. Because alpha is 1% and we want our p-value to be smaller than alpha, our decision rule is going to be to reject the null hypothesis at alpha equal 1% if the p-value of the sample statistic is less than or equal to 0.01. So you're going to compare your p-value to 0.01. And like every hypothesis test we've seen up to this point, every time we compare p to alpha, we want p to be smaller than alpha. So in the center you have 0. You're going to hope that the difference between the sample means is very negative, because the more negative it is, the more likely it's further away from 0, and the greater chance that we can reject the null hypothesis. Perform the experiment by analyzing the sample data. The symbol of the sample statistic is x bar 1 minus x bar 2. The value of the sample statistic, if we subtract x bar 1 minus x bar 2, 2.5 minus 2.6, we get negative 0.1. Okay, so remember that these two values, 2.5 and 2.6, were the sample means that were provided to you in the problem initially. So sample mean for the first group and then the sample mean for the second group. If you locate the negative 0.1 on the chart, the t-distribution, the bell curve, the t-distribution curve, you're going to see that it is negative, so it is on the left of 0. But you don't know how far on the left it really is until you take a look at its p-value. When we find its p-value, the p-value will be this area that goes down to negative infinity on the left, and then it stops at negative 0.01 on the right. So we hope that that p-value is smaller than alpha. It doesn't look like it's a lot smaller than 0. It doesn't look like it's far enough away from 0, but you don't know until you try it and look at the p-value. So going to your calculator, two-sample t-test, input the information that the problem provides for you. X bar 1 is 2.5, SX1 is 0.15, size of the sample is 20. And x bar 2 is 2.6, SX2 is 0.25. The size of the second sample was only 16 compared to 20. Scrolling down, you have to choose your direction. It's a test on the left, so you're going to use the less than mu sub 2, mu1 less than mu2. Pooled should always stay at yes and go down to calculate. And this gives us a p-value, which is what we are doing this for, of 0.072. No, actually, when we round this, it's 0.0730. 0.0730. Now that p-value, when you compare it to alpha, is larger than alpha. So the conclusion here is going to be to fail to reject the null hypothesis. Okay, here we go. Alpha is 1%. The p-value point is pink. Okay, so the alpha is in brown beneath it. The p-value is in pink, which overlaps alpha. The p-value is smaller. I'm sorry, the p-value is bigger than 1%. So our negative 0.1, the difference between the two sample means, isn't far enough away from 0 enough to reject the null hypothesis. So our result is not smaller than alpha. It's not smaller than 5% either, so it's not significant at all. So our conclusion is going to be to fail to reject HO at alpha equal 1%. Is the New York sports writer's claim justified? No, the New York sports writer's claim is not justified, and the reasoning is that when we fail to reject the null hypothesis, we cannot accept that the two populations have significantly different means. Okay, when we stated our null hypothesis, we stated that the two means were zero. The difference between the two means was zero, meaning that the two means were the same. If we don't reject that null hypothesis, then we can't say that the two means are different. We have to say that the same thing, that the difference between the two means is zero. So the population mean ERA for the American League pitchers is not significantly different than the population mean ERA for the National League pitchers. This last step is often the most difficult for students, so you often have to go back to the words of the problem and reread the words of the problem, and then it makes a little bit more sense if you can kind of understand what the null hypothesis is really stating and what it means to reject it. So that concludes the lecture on two-sample t-tests. We've now seen a total of 4 different hypothesis tests. This is the one that involves 2 populations and then the test uses 2 samples. So it's a little bit different than the previous ones, but there are lots of similarities. So if you do have a web work question on this topic, if you have any questions, please email me. I'll see you at the next lecture.